It is a cold and snowy day in Ithaca, New York, so a great day for a webinar. My name is Neil Mattson from Cornell University, and I get the opportunity to be our last speaker today. A little bit of an outline for my 25 minutes with you. We're going to talk about photoperiodic response groups, vegetables and herbs. And then, as one of the questions alluded to, how can we use this in a practical sense? So we'll talk about both strategies to keep leafy greens and herbs in a vegetative state, so not flowering. Then we're going to talk about lighting strategies for fruiting vegetables and using photoperiod as well for edible flowers. And then to try to tie in some of the concepts that Roberto was talking about with phytochrome and far red light. We'll talk about a case study research project that we did with edible pansies. So first of all, I'm going to show you a series of these 5 different tables. And Chris Curry did a very nice job of talking about the 5 major photoperiodic response groups that we divide plants into. And so what we have done here is, of the edible crops and herbs and veggies, is to look at group them into these photoperiodic response groups. So first are the obligate long day plants, and these are plants where long days are required to flower. And you'll see some of our more common herbs are listed here. So dill and cilantro, Greek oregano, sweet marjoram, a couple different mints, peppermint and spearmint, and then spinach as well. So these are crops that will flower when they're exposed to a longer day length. And we'll talk more about how to use this information in terms of scheduling. Then we have some crops that are also facultative long day plants. And so in this case, long days hasten flowering, so they flower at a smaller node number under long days than they would under short days. And a few examples here. So some of the dill that have been evaluated, instead of being obligate long day plants, they're actually facultative long day plants. So they will eventually flower with long days. They don't require long days to flower. Arugula or rocket is also noted as a long day plant, and it is not well researched. There may be differences between cultivar as to whether it's an obligate or facultative response. Lettuce also will flower under our long days of summertime, and we'll talk more about strategies to avoid early bolting in lettuce using both temperature and photoperiod. And then lemon thyme is another example of one of these facultative long day plants. So then if we switch to looking at those edibles and vegetables that require short days to flower, so these are the obligate short day plants, there's a relatively small number. So the 2 examples that I was able to find are sweet potato. And so if we want to get our sweet potato vines to flower, or if we want actually to get tubers to harvest, we need short day length for those crops. And then stevia, which is becoming very popular as an alternative to various sugar projects, is also a obligate short day plant. So in the case of stevia, if we wanted to market stevia in a potted plant and keep it vegetative, so it has lots of leaves for consumers to harvest, we would want to stay away from short day length and give it long days, either using day extension lighting or night interruption lighting, as our previous speakers have talked about. And I was able to find only one example of our common veggies and herbs that fall into the facultative short day plant response. So in this case, short days hasten flowering, but they're not required for flowering. And apparently the particular species of basil, Ocimum americanum, and then in particular cultivar blue spice, which has this nice shiny glossy leaves and beautiful blue or white flowers. Apparently it is the short days that hasten flowering but are not required for flowering. And then we have a fairly large number of crops that actually fit into the day neutral group. And I notice an error in my slide. It should say that day length does not impact flowering. So for these crops, many basil fit into this group. So our kind of standard Italian Genovese basil, as well as cinnamon basil also fits into this group. So there's nothing that we can do related to changing the day length or using night interruption lighting to get these crops to flower more quickly. Our standard oregano also fits into this group. And then interestingly, the three major kind of vine crops or fruiting vegetable crops that we're used to growing in greenhouses, peppers, cucumbers, and tomatoes, are also day neutral plants. So we can't manipulate day length to try to guide their flowering and subsequent fruiting. But we'll be talking in a little bit about strategies to promote flowering and yield of those crops, but not related to day length. And here's an example. So I mentioned that lime basil was a day neutral plant, and the way that we do research to learn that, this was provided graciously from Roberto Lopez at Michigan State. So they've been doing experiments with a fairly large variety of different species and cultivars of basil, but with lime basil exposed to day lengths of 9, 11, 12, 13, 14, 15, and 16 hours, as well as a night interruption treatment, which is the one on the right. And you see that there is indeed flowering under any of these treatments. So let's talk for a moment about some different lighting strategies to control precocious flowering, so avoid early flowering in some of the herbs, as well as in lettuce and spinach. So here we'll think about maybe a couple different standpoints. So one could be the grower that wants to continually grow these herbs in beds and cut and come again, so repeat harvest of them, and to not have them flower. So keep them vegetative so they keep producing their leaves. We'll also think of like a potted herb grower that wants to be able to market the herbs with a nice full plant that has filled out the container, but also not in flower, so the consumer can continue to harvest the leaves. And so if we think about some of our response groups, so cilantro, dill, and mint all fit into the long day plant group, and the obligate long day plants in particular. And so this means that they require long days in order to flower. So if our problem is early flowering, which reduces the size of a container plant, precociously flowering, so it's not as marketable, or our ability to repeat harvest. The solution then, right, is to avoid these long photo periods. So if the day length needs to be less than 12 hours. So if we're growing them in a sole source lighting application like the mint pictured here, that's being grown in a plant factory type application, one would want to keep the day length less than about 12 hours. And if one is growing then in a greenhouse, and we're going to have day lengths longer than 12 hours, between March 20th and September 20th, then we need to use blackout curtains during those hours of the nighttime, so that we have less than a 12-hour photo period. Now let's take a look at a couple of the leafy green crops, and so spinach in particular. And these series of photos come from spinach plants in our own research at Cornell. Actually, I teach a hydroponic food production course, and we tried growing spinach seedlings and then transplanting them into an NFT system. And we got them, they ended up flowering. And so that caused us to do a little more research into this. So the symptoms of spinach that are bolting, of course, would be that elongated main stem, versus typically when the plant is vegetative, the leaves grow in a nice rosette, compact form. Interestingly, the leaves also change shape as the plant turns into its reproductive mode. And so instead of seeing oval-shaped leaves, we get arrow-shaped leaves. You can kind of see that here in the picture, like in the top right. And then spinach flowers are a very interesting flower. So you see these white fan-shaped flowers that appear at each of the the internodes where the leaves connect to the stem. So that's bolting in spinach. The causes would be for a couple different reasons. One is that spinach is indeed a long day plant, an obligate long day plant. The critical photoperiod is reported in the scientific literature to be about 13 to 14 hours, depending on cultivar. So if we keep day length less than that 13, 14 hours, we can help keep the plants vegetative. Warm temperatures also compound the problem. And so like air temperatures, above about 80 degrees Fahrenheit are going to start to impact bolting as well and contribute to bolting. And in general, plants that are grown too long. So if one is growing more of a baby leaf crop and doing a quick turn, the critical photoperiod is not going to be as important. But if we have that compounding effect of warm temperatures, that long photoperiod, and then growing the plants for a longer period of time, they're going to bolt. And so solutions would be growing under cool temperatures, having a photoperiod less than 12 hours. And there's a nice paper about some research in Japan where they actually looked at growing spinach seedlings in a controlled environment before transplanting into the field. And during the seedling stage, they grew plants under a temperature of 68 degrees Fahrenheit with a 12-hour photoperiod. And then those were transplanted into a field under summer type conditions in Japan. And they went back and looked at the plants 14 days later, and they found that seedlings grown under that cool temperature regime with the short photoperiod, only 4% of them had bolted, versus they had a control, which was the typical seedling production method, where those plants had received 15.5-hour photoperiod, as well as warm ambient air temperatures. They said going up to about 90 degrees in the article I wrote, but air temperatures varying between 70 to 90 degrees in their ambient temperature. And so those control plants, 86% of them had bolted by 14 days after transplanting. So again, just the point of cool temperatures and short day length to keep our spinach plants vegetative. And this is what it looks like when we grow baby leaf spinach in our research trials at Cornell University, and we do things right. So we germinate the seeds for 3 to 4 days in a growth chamber, and then we finish them floating them in a hydroponic pond for 14 days. And so harvest them when their leaves are about 2.5 inches wide. And so when temperatures are cool, we find that we can keep photoperiod long, and we're harvesting young enough that we don't run into bolting in this particular case. So then a similar problem with lettuce. Again, the symptoms of bolting in lettuce would be an elongated main stem. As well, you can have poor head development. So instead of having a compact lettuce head, you're starting to get long internode elongation. So you won't be able to get that compact marketable head of lettuce. And the causes of lettuce bolting, again, lettuce is a long day plant, but it is not an obligate long day plant. So it's facultative, meaning that long days can favor flowering, but they'll still flower even in the absence of long days. And then in looking in the literature and past experiences with growers, it would seem that warm temperatures are really the main cause of bolting. So we have some small ability to manipulate bolting using shorter day length, but essentially this becomes a problem when we have repeated exposure, so several days of warm air temperatures, say greater than 80 degrees Fahrenheit. So our main solutions for bolting and lettuce are not really manipulating the day length, but instead using cool air temperatures, so less than, say, 80 degrees Fahrenheit. If it's difficult to control air temperature, so if we're growing lettuce in a greenhouse in the summertime, what has been found to be effective in the literature is actually chilling the root zone. So if you're growing in, say, a pond hydroponics, a raft pond hydroponics application, If you can chill the water temperature in the pond to about 65 degrees Fahrenheit, that's been reported to delay bolting by several days, even if air temperature is still 80 degrees, even up to 90 degrees. And then I think a real opportunity for us greenhouse growers is actually cultivar selection. So there was a paper back from 1995 that looked at dozens of varieties of lettuce, grew them under a 16-hour photoperiod, so under an inductive long day photoperiod. And it found that days to bolting really varied highly based on cultivar. So on the low end, some cultivars bolted at 32 days, while other cultivars took 128 days to bolt. In terms of overall lighting of leafy greens, we talked about lettuce and how they are facultative long day plants. But typically, if we're harvesting the plants young enough, day length isn't the main problem causing bolting, it's actually temperature. And so what that means is typically for growing leafy greens, we can use lighting over long days and continuous lighting. So if we're growing in a sole source lighting application, it's common to light for, say, an 18-hour period. We've even in our research had success lighting 24/7, so continuous lighting with these vegetative crops, so long as we're avoiding excessive temperatures and harvesting them when you're young enough. And what continuous lighting or long day length allows you to do is if you're trying to achieve a given daily light integral target, is you can achieve that using a lower amount of light fixtures in your greenhouse or in your sole source lighting application. So an example of that, let's say we wanted to reach 15 mole per meter squared per day DLI target. And let's say we have a sole source lighting application, so we need to install lighting fixtures, whether they be fluorescent or LED or high pressure sodium. And if we could only have those on for 10 hours a day, we would need to install lighting capacity so as to deliver 400 micromoles per meter squared per second of instantaneous light. If we could instead have the lights on for twice that time for 20 hours a day, then we could reach our DLI target with having half of the lighting capacity installed, so that our instantaneous lighting target would be 200 micromoles per meter squared per second. And then let me mention lighting vine crops. So we mentioned that for cucumbers, peppers, and tomatoes, that photoperiod does not impact flowering and therefore fruiting. So it's really the total quantity of light, the daily light integral, is what's important. So in terms of the target daily light integral requirements, these are all fairly high light requiring crops. So commonly for bedding plants and potted plants, we're looking at, say, 10 to 12 moles of light minimum each day to get good crop quality. For cucumbers, tomatoes, and peppers as examples, essentially for each addition of 1% of light, we get 1% more yield. And kind of the minimum thresholds that we're looking at are about 15 moles per meter squared per day of light for cucumbers and 20 moles per day for tomatoes and sweet peppers. And then, of course, more light is better, right? So even up to 30 moles of light or above is going to give you highest yielding plants. So then again, if we think about the number of hours a day that we can have the lights on, and let's say that we have an installed lighting capacity of 150 micromoles per meter squared per second of supplemental light, then the hours a day that we have them on has a huge influence, right? A linear influence on the daily light integral. So if we have them on for 8 hours, we're only getting 4.3 moles per day. But if we had them on for 20 hours, we'd be getting 10.8 moles. So if we had an example where maybe sunlight is giving us 10 moles of light, and then we have our fixtures on for 20 hours a day, then we're getting an additional 11 moles of light. And so we'd be getting into that above our minimum thresholds for good crop yield for these crops. And then you might look at, say, the 24 hours a day and say, if I have them on 24/7 continuously, I could get 13 moles of light. what I want to say then is caution for tomatoes and peppers. It's actually, there has been a lot of research looking into physiological disorders that result from continuous lighting. So we actually can't light these crops 24 hours a day, 7 days a week. With tomatoes, they need about a 6-hour dark period, and peppers require about a 4-hour dark period. And the reason that we say this is because there's a large literature around physiological disorders if the day length is too long. So if we have that day length more than about 18 hours for tomatoes or more than about 20 hours for peppers, what we find is that leaves turn yellow and get brown spots on them, so leaf chlorosis, reduced plant size, and then reduced yield. And scientists that have looked into this issue, looks like without that dark period, what is happening is that, so the leaves accumulate carbohydrates as they photosynthesize during the light hours, and then the dark period is a signal to translocate carbohydrates to the fruit. And without this dark period, there tends to be starch accumulation in the leaves, which then leads to this physiological disorder, as well as lower yields. So just a reminder then with tomatoes and peppers to have that dark period. So a couple other points to cover. So we're seeing increased interest in edible flowers. And as was talked about during the question period with Christopher Curry's presentation, is that then we can take the same response group information and look at what it takes to induce flowering in these different species and apply those inductive lighting treatments. So if we look at, I tried to pick some of the more common edible flowers here. So snapdragon, a couple different types of begonia, a couple different types of marigold and calendula, bachelor buttons, pinks, nasturtiums, and pansies. And of this grouping that I have listed here, I highlighted the species that were long day plants, either facultative long day plants or obligate long day plants. So many of these edible flowers, we need to give them a long day length to induce earlier flowering, or some of them, such as tuberous begonias, require long day lengths to flower. And then wax begonia does not depend on day length for flowering, as well as French marigold. And then African marigold is a facultative short day plant, so short day lengths lead to earlier flowering. And one example of this photo happens to come from my master's research back in the day with John Irwin at the University of Minnesota. So growing bachelor buttons under an 8-hour photo period versus natural day length plus night interruption lighting. So indeed, it did take long days to get these plants to flower. So under short days, the plants took more than 112 days to flower. Under long days, the plants flowered in 45 days. So it could start harvesting our edible flowers in a third of the time by using those long day photo periods. All right, and then the last point I wanted to mention was some research that we have done with far red light and edible pansies. And to connect it back to Roberto's talk, he showed this excellent graph with the two forms of phytochrome. And for the long day plants, the point that he made was that we need an accumulation of phytochrome in the far red form to induce flowering. So again, for long day plants, that high PFR form induces flowering. And so this is an experiment. A couple of years ago, I had the opportunity to do a short sabbatical at the University of California, Davis with Heiner Leith and another visiting scientist, Won-Soon Kim. And there are photos of us. We looked at pansy cultivar, so it was Viola Sorbet in this case, from Pan American. Seedlings were grown under white LEDs at 180 micromoles photosynthetically active light for an 18-hour photoperiod. These were transplanted into 3-inch pots. And then after the seedling stage, we grew them on for 42 days under a couple different light treatments, and then harvested flowers over time. So here we're thinking about growing this viola for edible flowers. And so the 2 lighting treatments that we had were, our control was a red-blue treatment. So we had 1/3 of our light was from blue light, 60 micromoles, and then 120 micromoles of light came from red light. And then our experimental treatment was, we had that same background light, so we still had the same amounts of red and blue light, and thus the same amount of photosynthetically active radiation, 180 micromoles per meter squared per second. But then we added an additional 50 micromoles of light from far red light. And to show you what the light spectrum looked like, the kind of pink dashes that you see here are the red-blue treatment. So you do indeed see the pink, the peak in blue, and again a peak in red. And then the additional light treatment that had the far red light are these red dots. And so we see the same amount of red and blue light, but then we see this additional peak here at about 740 nanometers, adding far red light. And this is what these looked like. So they were these individual bars, and we periodically had these far red light bars. And so the interesting thing, so I have this arrow here pointing out the far red light bars. Far red light is not really visible to our eyes, right? And so we could measure it and quantify that peak with a spectroradiometer, but not really detect that with our naked eyes. And then the interesting thing, so here's the harvest data. So this is cumulative flower number during a 42-day treatment period. So the plants were harvested 6 times during this treatment period. And the control treatment with just red and blue light is on the left. And the treatment with far red light is on the right. And then again, the bar graphs show we had about 30 flowers total harvested under the red-blue treatment. And about twice as many flowers, 55 flowers per plant harvested in the far red light treatment. So indeed, far red light, in this case, we didn't look at earliness to flower, but we looked at flower induction over time. So we had about twice the number of harvestable flowers. The interesting thing to me is if you look at the plant form, the plant height, far red light does, of course, give us a taller plant. And so maybe the plant on the right would not be marketable from the standpoint of selling it as a flowering bedding plant. And that plant on the left would be a nice marketable flowering bedding plant. But in terms of edible flower production, the far red light was beneficial in this application. With that, I want to point out a collaborative group that has been formed. So at Cornell University, with collaborators at Rensselaer Polytechnic Institute, their lighting enabled systems and applications unit that has great engineers working with designing LED lighting systems, traditionally for humans and now for plants, as well as AJ Both at Rutgers University. We formed this group called Glaze, or Greenhouse Lighting and Systems Engineering. And you can find out more information about our group and our research projects at glaze.cals.cornell.edu. So again, I'd like to acknowledge the sponsor for the webinar today, PL Light Systems. And with that, I'd like to thank you, and I'll invite any questions.